Hello, and welcome to the TI Precision Labs video covering how a PCB layer stack-up impacts the system EMC performance. This is part of a larger series on PCB layout for good EMC. The series is specifically intended to cover mixed signal designs where the digital signals are less than 100 MHz and the clock rise times are greater than 1 nanosecond. This video looks at how changing the order and function of the layers can have significant impacts on performance. Let's get started by reviewing some PCB terminology. This slide provides a reminder of some key definitions for PCB construction. This example covers a 4-layer board, but it could be applied to higher layer counts. The core of a PCB is a rigid fiberglass panel with copper foil on top and bottom. The core is basically a 2-layer board. To expand to higher layer counts, a thin sheet of fiberglass with glue, called prepreg, is used to attach a top and bottom foil. This example PCB shows very common thicknesses. For example, a 62 mm board thickness is considered to be a standard PCB thickness, and a 7 mm prepreg thickness is very common. Normally the core is fairly thick and the prepreg is thin. Thus, the top layer is very close to the top of the core and the bottom layer is very close to the bottom of the core. For good EMI performance, the signal layers should be as close as possible to their associated ground return layer. Using the top layer as a signal layer and the adjacent inner layer as a ground return is a good choice because the prepreg is generally thin. For good power supply decoupling, it is helpful to keep the power and ground layer close together as well. If the core is used for the power plane and ground plane, it can be difficult to keep the spacing tight as the core is usually a thicker material. Here we compare different stack-ups to see which is best. The worst stack-ups use 2 adjacent layers with signals on each layer. In this case, the 2 signals can interfere with each other and the ground reference is typically far from the signals, making the return current spread out. A common approach used on 4-layer boards is to use power and ground as internal layers and have signals on the outer layers. The power layer on the bottom will act as a return path for signals on the bottom. One possible issue with this approach is that the power layer may be split into multiple power rails. In this case, there will be discontinuities or slots in the return path and stitching capacitors will be required to bridge the gap. Also, when transitioning from the top layer to the bottom layer, the return path will need to transition from ground to power, and this will cause RF emissions. The best approach for good EMI on a 4-layer board is to use 2 internal ground planes. In this case, signals would be assigned to the top layer and power and signals would be on the bottom layer. This method has the advantage of keeping the power rails very close to the ground return path, which will improve decoupling. This method also eliminates the need for stitching capacitors as the ground return is solid, whereas the power plane in the previous example was split to accommodate multiple power rails. Also, when signals on the top and bottom transition layers, the 2 internal layers are connected together with stitching vias, so emissions are minimal. The 6-layer and higher layer count printed circuit boards follow the same principles. In short, you never want signal layers without adjacent ground return paths. Also, keeping power close to ground will improve decoupling. This example shows how using a power layer as an adjacent signal layer can cause problems. This method can work, but you will need to be careful to avoid routing signals above splits in the power plane. In this example, power is split into a 3.3 volt digital plane and a 5 volt analog plane. The design on the left can create RF emissions because the digital signal is routed over splits in the return path. On the right, the layout was adjusted to keep a continuous digital power plane beneath the I/O lines. For this design, the return current will flow through the digital 3.3 volt power plane and not the ground plane. This slide shows how 2 internal ground planes can be used in a 4-layer board. In this case, most of the signals will be routed on the top layer and the power planes are on the bottom. Some signal traces can be routed on the bottom, but the majority of the bottom layer is dedicated to power. This stack-up has the advantage of keeping the power plane close to its ground return, which will improve decoupling as the AC impedance between the power and ground are low. Also, signals transitioning from the top layer to the bottom layer will not require stitching capacitors. The example from the last slide can be modified so that power is routed as thick traces rather than planes. If the transient currents on the power rails are not significant, routing power is a reasonable approach. The advantage of this approach over the large power planes is that more space is available for signal routing on the bottom layer. Crosstalk is the interference of one signal with another. Crosstalk can be between two digital traces, or it can be a transient coupling into an analog signal. Here is an example of a two-layer board. For this type of board, the best stack-up is to put power and signal on the top layer and use the bottom layer as a solid ground plane. However, it can often be difficult to route the board with all signals and power on the top, so frequently some signals will be routed on the bottom. What are some common issues associated with this kind of stack-up? One significant issue with two-layer boards occurs because some traces need to be routed on the bottom layer. The trace on the bottom causes a discontinuity in the ground path. When signals on the top layer pass over this discontinuity, the ground return currents are forced to route around the split and RF emissions happen. Another issue occurs because the top and bottom layers are physically separated by a significant distance. A typical board thickness for a two-layer board is 62 mils. This thickness is significantly greater than the distance between the top layer and the core on a four-layer board. Increasing the separation between layers will cause the field beneath the trace to spread out. Remember Mr. EMI? He will conform to the distance between the top and bottom of the waveguide. Spreading out of the fields will increase the crosstalk between digital and sensitive analog traces. Of course, if the two-layer board is made to be thin, then this problem is minimized. But this may not be practical from a mechanical strength perspective. That concludes this video. Thanks for watching. Please try the quiz to check your understanding of this video's content. Question 1. What are some potential problems with the stack-up below? The correct answer is F. Answers C and D are problems. Keeping the ground and power close together reduce the high frequency impedance between the planes. This low impedance will effectively short out the power supply noise. In this case, the power and ground are separated by a large distance, so the high-speed decoupling will be degraded. Also, the power plane is split. This split can cause issues if signals are driven across the split. Question 2. What are some potential problems with the stack-up below? The correct answer is A. The two adjacent signals do not have an adjacent ground return, so they will potentially interfere with each other. In this case, the signals on the top two layers will reference the ground plane, and all the return currents will mix, causing crosstalk. On the bottom two layers, the signals are referenced to the power plane, and again, the return currents will mix. Also, the bottom layer has a split, which will cause issues if signals cross the split. That's all for today's video. Thanks for watching.